Welcome back to qubit-lab.ch. In the previous video, we set the stage. Why quantum chemistry is a natural target for quantum computers. And we used a battery R&D example to make it concrete. We also walked from orbitals to the electronic Hamiltonian, because that Hamiltonian is the mathematical object we need before any quantum algorithm can run. In this second video, we focus on the algorithms themselves. I'll compare the main approaches side by side, and I'll be explicit about what's realistic on today's NISQ devices versus what becomes attractive once we have fault-tolerant quantum computers. Here's the landscape for our ground state energy problem. In the last video, we already saw this overview, but let me summarize it once more. At the top, we have the NISQ options, VQE as the baseline, and ADAPT-VQE as the more adaptive variant, usually trading fewer ansatz assumptions for more measurements. At the bottom, we have the fault-tolerant route, quantum phase estimation, where you either build the time evolution with Trotterization, which introduces a discretization versus depth trade-off, or you switch to Qubitization, which avoids the Trotter step size error but needs block encoding. Now we'll use this as our roadmap and zoom in, starting with what's practical on NISQ today, and then looking at what changes once fault-tolerant hardware is available. Let's begin with VQE, the workhorse hybrid algorithm for the NISQ era. We start from the molecule's Hamiltonian H, already mapped to qubits as a weighted sum of Pauli strings. VQE does not solve the eigenvalue problem directly. Instead, we define an ansatz state, psi of theta, a parametrized family of candidate wave functions. Theta are the knobs that control the shape of that wave function. In practice, psi of theta is prepared by running a parametrized circuit on a simple reference state, usually all zeros. But the object we optimize is the state itself. On the quantum device, we estimate the energy E of theta equals bra psi of theta, H, ket psi of theta. Because H is a sum of Pauli terms, we measure those Pauli strings many times, often grouping commuting terms, and combine the results using the coefficients of H. A classical optimizer then proposes a new theta. We prepare psi of theta again, remeasure the energy, and repeat until the energy converges. The final theta gives our best estimate of the ground state energy and the corresponding approximate ground state wave function. With ADAPT-VQE, the goal is the same as VQE. Minimize the energy of a trial state, E of theta equals bra psi of theta, H, ket psi of theta. The big change is how we choose psi of theta. In standard VQE, we pick a fixed circuit layout up front and only tune its parameters. ADAPT-VQE starts much smaller, from a simple reference state, and then builds the ansatz as it goes. We begin with a reference wave function, typically something Hartree-Fock-like, and an operator pool, a menu of physically motivated excitation operators. Then we ask a very specific question. Which operator, if added next, would decrease the energy the most? To answer that, we estimate a gradient signal for each candidate operator on the current state, pick the one with the largest magnitude, append it to the ansatz, and re-optimize all parameters with the classical optimizer. So the loop becomes measure gradients to choose the next operator, grow the circuit by one layer, re-optimize the parameters, and stop when all gradients are small, meaning there is no operator left that can significantly improve the energy. Compared to VQE, it is more measurement heavy, because you have to evaluate many gradients per loop, but it can converge in a more targeted way, especially in chemically relevant spaces, where a fixed ansatz might be either too small to be accurate or too large to be trainable. We now move from VQE style energy estimates to quantum phase estimation, which is the fault-tolerant route to high precision. We start with the molecule's Hamiltonian H, but QPE needs a unitary, so we use, for instance, time evolution, e to the power minus I times h times t. If the state is an energy eigenstate with energy E, applying U of t only adds a phase. U of t applied to psi gives back the same state, scaled by a phase factor e to the minus iet. So the phase phi directly encodes the energy. QPE estimates that phase by applying controlled powers U of t to the power 2 to the k, then an inverse quantum Fourier transform, QFT. QFT is a well-known standard circuit in quantum computing. Finally, we map phase back to energy using that E is equal to minus phi divided by t, taking care of the 2 pi wraparound using a known energy range. Trotterization is a variant using QPE. The approach is the same as before, but now we focus on how we build the unitary. The time evolution U of t is unitary. Here, we approximate it with the first or second order Trotter formula. Repeating these Trotter steps improves accuracy, but it also increases circuit depth. That's Trotterization. So the trade-off is, more Trotter steps means better accuracy, but much deeper circuits. Everything after that is unchanged. QPE still uses controlled powers U of t to the power of 2 to the power of k, and we map the measured phase back to an energy with the usual 2 pi wraparound caveat. For qubitization, another variant of QPE, we avoid Trotter step size error by using a walk operator whose eigenphases encode energy. This happens in 2 steps. First, build a block-encoding unitary representation of h divided by alpha, called u, and then use u to define a walk operator w, which delivers the required properties. Specifically, step 1. We rewrite the Hamiltonian as a weighted sum of Pauli strings, then build a block encoding of h divided by alpha using the LCU preselect prep dagger construction. Step 2. From that block encoding, we build a new unitary, the walk operator w. The energy is no longer encoded as minus e times t directly. Instead, QPE estimates an angle theta of w, and we map back via e equal to alpha cosine of theta. So, compared to Trotterization, a more sophisticated setup, no Trotter discretization error, and it's the approach with the best known asymptotic scaling once you have fault-tolerant hardware. That wraps up video 2. We now have the algorithm landscape for ground state energy, what is realistic on NISQ today with VQE and ADAPT-VQE, and what becomes attractive later with phase estimation via Trotterization and Qubitization. For more material on quantum computing in business, finance, and chemistry, visit qubit-lab.ch. Thanks for watching and have a great day.